Once we get beyond helium, we can see that we have 3 attractive terms and 3 repulsive terms in our Hamiltonian for 3 electrons. And when we go to 4 electrons, we're going to have 6 different electron-electron repulsion terms and 4 different coordinates, etc., etc. So as we build up these multi-electron atoms and add more and more electrons and more protons to the nucleus, the problem gets more and more complicated. So to simplify the problem, what we're going to do is assume that each electron is repelled by an average potential energy from all n-1 other electrons in the atom. So we're going to try to find an average field or an average potential energy that affects each of these electrons in the atom. This average field is called a self-consistent field that we're going to use to think about how that electron-electron repulsion works in these multi-electron atoms. So our full Hamiltonian then becomes a Hamiltonian for each electron. To take care of the electron-electron repulsion, we're going to add in that average repulsive potential into our Hamiltonian. And it's that average repulsive potential that is going to take care of all of the electron-electron repulsions that each electron feels from the other n-1 electrons. This then allows us to separate our Hamiltonian into n Hamiltonians, one for each electron. So the Hamiltonian for electron 1 would be the kinetic energy for electron 1 plus the the attractive potential between electron 1 and the nucleus, which depends just on the distance between electron 1 and the nucleus. And then it's going to be minus this repulsive potential that is dependent only on where electron 1 is in the average field of the other electrons. So this average field is going to depend on where those electrons are on average, but in terms of thinking about how it affects electron 1, it's only going to depend on the distance, on the position of electron 1 in that field. And so I can write one of these for each electron. And now, if I can separate this, then my full wave function is the wave function for electron 1 times the wave function for electron 2 times the wave function for electron 3 and so forth and so on. And my energy, my total energy then, is the energy for electron 1 plus the energy for electron 2 plus the energy for electron 3 plus and so forth and so on. We're going to need to solve this problem iteratively. So let's imagine that we have a ground state carbon atom that has a 1s2, 2s2, 2p2 configuration. And we're going to try to find the orbital energy for the 1s electron, one of the 1s electrons. So this 1s electron is affected by the other 1s electron, the 2s electrons, and the 2p electrons. And so we're going to try to find, or we're going to calculate an average repulsive potential based on the probability distributions of all these n-1 other electrons. And so we need to write some repulsive potential, some average repulsive potential, but that's going to depend on the probability distribution for the 1s, the probability distribution for the 2s electrons, and the probability distribution for the 2p electrons. Remember that the probability is psi star psi, or I've just written that as psi squared. So those probabilities, where those electrons are, is going to affect what that field or that repulsive potential looks like. So that's the first thing. We figure out what that repulsive potential looks like. And then we find the minimum expectation value for the electron 1 where we let each electron have its own effective nuclear charge. And so Z effective 1 is the effective charge on the nucleus for electron 1. So we do this for each electron and minimize the orbital energy, the energy that that electron contributes to the total energy of the atom. And then that gives us a new, better function for the 1s orbital, the 2s orbital, and the 2p orbital. So now because these things are different, they've changed, that means that our average repulsive potential is also changed. Now, this average repulsive potential that we used to solve this problem the first time doesn't work anymore because now we have a new average potential. So now we need to calculate a new average potential and repeat this process. Find the new minimum orbital energies for each of the electrons, and then we just keep repeating that until the average potential that we calculate stays basically the same, or we say it converges between one iteration and the next. And once we've found that average potential, where each time we iterate, we get the same answer, we say that the problem has converged, and that average potential gives us our self-consistent field. So notice that it's self-consistent because every time we iterate, we get the same answer. So our self-consistent field is the final average potential that we get out of this. And the energy, the total energy of the atom, is the orbital energies for each electron. So the energy of each electron that gives us that minimum energy in that self-consistent field. We call these the orbital energies because they are the amount of energy that each electron contributes to the total energy of the atom in that particular electron configuration. So in this case, in the ground state, since we started with a ground state configuration. So lucky for us, someone has done these calculations for most of the atoms in the periodic table. And so here we can see the first row atoms, and you can see the orbital energies for the different orbitals. Notice that for helium, the orbital energies for the 1s are both the same, meaning that their Z effectives are the same. But for lithium, the 1s orbitals have slightly different Z effective. The 1s electrons have slightly different Z effectives, and the 2s orbital has a very different Z effective. It has a very different orbital energy. And so if you add up all of these orbital energies, you get the total Hartree-Fock energy for that configuration of the atom. So these are all ground state configurations. And then don't worry about this row right here. That's a slightly different approximation that you can use. And then the experimental value is given so you can see how close you are, the Hartree-Fock approximation is to the actual experimental value. Recall that for the hydrogen atom, we can write the energy of any n level as equal to Z squared times units of Hartree, so times the Hartree energy divided by 2n squared. And so each of these orbital energies can be used to calculate a Z effective for each of these particular electrons. So if we know what n is, so n equals 1, and these energies are all in Hartrees, so we just take the energy of the orbital times 2 times n squared and take the square root of that to get our Z effective. So Z effective can be calculated for each of these particular orbital energies. So each of these electrons has its own Z effective, and we can get that by taking the square root of 2n squared times the orbital energy given in the table.